So looking at waves, we need to look at a few pieces of terminology. The first one we're going to look at is equilibrium point. What the equilibrium point is, it's the rest position of the medium. So if we're looking at our wave, this black line, this is what we would be at if we didn't have waves going on. This is where we would be sitting on the medium. So we call that the equilibrium point. The next piece of terminology that we need to look at is crests. We've already looked in most of the waves what crests are. And what they are is just where the medium rises above the equilibrium position. So in our waves, as soon as we get above the equilibrium, this is the crest. The next terminology that we have is troughs. Troughs are where the medium fall below the equilibrium position. So now when our wave comes down below, that's in a trough. So we have a crest, a trough, and when they're in the middle, that's the equilibrium position. The next one is the wavelength. The wavelength is one complete cycle of the wave. So if we have one complete cycle of the wave, like we learned on the last page, that would be if we go from one top of the crest to the next top of the crest, or one part of the trough to the next part of the trough. It's if we get one full complete cycle of the wave. A piece of terminology that we haven't looked at yet is the displacement. What the displacement is, it's the distance from the equilibrium point to the wave. So if I take any point on the wave, for example, if I take right there, the distance from the equilibrium point, we call that the displacement. What the amplitude is, it's the maximum displacement from the equilibrium position. So if it's the maximum displacement from the equilibrium position, that means it's going to be at the very peak of your crest. That's the furthest away you're going to get from your equilibrium position. And that you're going to call the amplitude. The next one is pulse. Pulse often gets confused with wavelength for what it is. But what pulse is, it's only half of the wavelength. So that means if you move from one equilibrium point to being at the next equilibrium point, well, we're going to learn the term for that coming up, that's called one node to the next node, that is only half of a wavelength, or that's one pulse. Same if we're going through the trough from one to the other, that's one pulse. Period is a terminology that we've already learned last unit. Period is the time it takes for the wave to move one wavelength. So to get from one crest to the next, the time it takes is the period. To get from your beginning node to the next one on the way up, that is one period, the amount of time that it takes. Frequency is almost could be thought of as the reverse. It's the number of wavelengths that pass a given point in a second. So if that given point is, again, here on the way up, each time it comes by and hits that point, that's 1 hertz. Alright, it comes by and hits again, that's another one. So if it gets through 2 full wavelengths in a second, your frequency would be 2 hertz. If it gets through 36 complete wavelengths in 1 second, your hertz would be 36 hertz. The last two more major terminologies you're going to need to know are in phase and out of phase. If something is in phase, it's at the same point of motion. So if I'm going up, if I call this point A, on my next wave, if I'm at the same point, point B, and my third wave even the same, that means A, B, and C are all in motion. Or, sorry, are all in phase. They have the same displacement and the same time. If they're out of phase, it's just almost the opposite. If they are not at the same point of motion, so if A is still in the same spot, but now B is somewhere down here, C is somewhere up here, A, B, and C are all out of phase. They're not at the same point of motion, are out of phase. So mathematically, all waves are going to obey what we call the universal wave equation. What the universal wave equation is it is the velocity of the wave is equal to the wavelength times the frequency. That is a pretty simple formula that you are going to have on your formula sheet. Alright, so you don't need to memorize that one, but it is going to come in handy. So in this first example, we have light waves traveling at 3.00 times 10 to the 8 meters per second. Find the wavelength of a light ray that has a frequency of 7.92 times 10 to the 14 hertz. So as I do in all of the examples I give you and all the questions I do, I like to write down the information I'm given first. I know that the velocity of the light wave is 3.00 times 10 to the 8 meters per second. We want to find what is the wavelength, and we know that the frequency is 7.92 times 10 to the 14 hertz. So using our universal wave equation, velocity is equal to wavelength times frequency. We want to rearrange and solve for wavelength. To do that, we're going to divide both sides by frequency. We'll cancel out, and we're left with wavelength is equal to velocity over frequency. Since we have that information, we can just plug in and solve. That's going to be equal to 3.00 times 10 to the 8 meters per second over 7.92 times 10 to the 14 hertz. That gives us a final wavelength, when you plug that into your calculator, of 3.79 times 10 to the negative 7 meters. Let's try another example. In this example, we have a wave that has a speed of 0.305 meters per second and a wavelength of 3.7 meters. What is the period? Again, the information that we're given is the velocity is equal to 305 meters per second. Wavelength is equal to 3.7 meters, and we want to solve what is the period. So remember, to solve for period is equal to 1 over the frequency. We can use this information here and the universal wave equation to find what is frequency. To do that, I'm not even going to give you the beginning. Actually, maybe I will. Velocity is equal to wavelength times frequency. That's our universal wave equation. We want to rearrange for frequency, giving us frequency is equal to velocity over wavelength, which is equal to 0.305 meters per second over 3.7 meters. That means our frequency is equal to 0.0824 hertz. Remember, this question wants to solve what is the period. So now that we know the frequency, we can plug this information in over here to solve for period. Period is equal to 1 over 0.0824 hertz. So your period is going to be equal to 12 seconds. Alright, let's do one last example together, and then there will be some more for you to try on your own. So you have 12 complete waves are on a rope when a person holding the rope shakes the end with a frequency of 6.5 hertz. If the rope is 9.2 meters long, find the speed and the period of the waves. So again, let's figure out what information is given to us. We are given that we have 12 complete waves. So we have 12 complete waves. Or our wavelength is equal to 12. We're going to have 12 wavelengths. In that time, there is a frequency of 6.5 hertz, and the length of the rope is equal to 9.2 meters. What we want to find is the speed and the period of the waves. So let's first solve for period, because solving for period is pretty easy with the information we're given. Period is equal to 1 over the frequency. We know the frequency, so all we need to do is plug in and solve. That's equal to 1 over 6.5 hertz, which is equal to 0.15 seconds. The next one we need to solve for is what is the velocity. So our universal wave equation is velocity is equal to wavelength times frequency. We have frequency, but to solve for wavelength, we have 12 wavelengths currently. When we have 12 wavelengths, they are equal to 9.2 meters on the rope. So to get wavelength by itself, or to solve for just one wavelength, we're going to divide that 9.2 meters by 12. That means our wavelength is equal to 0.767 meters. Again, the information we're given that there's 12 wavelengths are equal to 9.2 meters. When we're using the universal wave equation, we only want one wavelength. So if we split those 12 wavelengths up into 12, or in other words, we find out the distance of just one wavelength, it's 0.767 meters. So when we plug this in now, we have wavelength and we have frequency. So your speed is going to be 0.767 meters times 6.5 hertz. Meaning your speed is going to be 5.0 meters per second.